Hello again, everyone. I am Dr. Dasgupta from the Naval Research Laboratory. Today we are going to start with the second of our three-part lecture series at the TJ-AIML Club. The topic of today's lecture is reinforcement learning. This is going to be the outline of my talk. Now, as you know, reinforcement learning is a type of machine learning. The other two types of machine learning, supervised learning and unsupervised learning, they basically learn a hypothesis that's consistent with the distribution of the data that's used to train the algorithm. In contrast, reinforcement learning is a reward-based learning algorithm. So what is this reward? It's very similar to what is done to teach a dog some new tricks. For example, if you want the dog to learn how to kneel at a certain command, every time the dog kneels at the command, you give it a treat. On the other hand, upon hearing the command, if the dog does not kneel, then you do not give the reward. It's the same idea for agents as well. If the agent does something, in other words, if the agent takes an action that helps it reach towards its goal or solve the problem at hand, then it's given a virtual reward, a number-based reward. On the other hand, if it does not do something that helps it reach towards the solution, if its action is not helping it reach towards the action, then it gets a negative reward. Now, this reward framework is formalized by something called a policy. A policy is basically a function that the agent solves inside the reinforcement learning algorithm, which tells it what to do when. So basically, a policy is a mapping from the states or the different situations that the agent can end up in. It's a mapping from the states to the actions. In other words, what the agent can or cannot do. So let's delve a bit further into the reinforcement learning framework. Reinforcement learning is based upon a math formalism. It's called Markov decision processes, or MDPs for short. Now, MDPs comprise of four attributes. S is a state space, or what the states of the problem are, what the different situations that the agent can end up in. A is the action space, or what are the things that the agent can do. T is a transition function. It's also called the model of the problem. And basically it says if the agent takes a certain action at a certain state, what next state does the agent and the model of the problem end up in? And finally, R is a reward function. This ties back to the reward framework for reinforcement learning that we were talking about. And it basically specified what reward the agent gets when it reaches a certain state. The output of the MDP is called a policy, denoted by pi. And pi is basically a mapping from the state space to the action space. In other words, it says what is the best action that the agent should take at every state. Let's look at an example of an MDP. Here I'm showing a grid world, an 8x8 set of cells. There's a robot shown by the green circle towards the bottom left corner, and its objective is to reach the cell denoted by G. There are four components of the FDP, S, A, T, R. The state space, S, in this case, is basically the 8x8 set of cells that comprise the grid world. The robot occupies one of those cells, denoted by the coordinate 1, 1. The goal is at a certain coordinate. In this grid, it's at 7, 7. And there are two obstacles shown by the red colored blocks. The action space of the agent basically is the actions or the movements that the robot can do. And here the robot can move either north, south, east or west from each cell. The fourth component of the MDP is the transition function or the model. For example, a transition for the agent could be when it's at cell 1, 1, it could do an action north, and that would take it one cell upwards to the cell 1, 2. So we write that as T of 1, 1 and N would take it to 1, 2. T could be a probabilistic function too, which is it gives a certain probability of the agent reaching a certain cell by doing a certain action. Details are given on the slide. Finally, the fourth component of the MDP is the reward function R. And here I give a simple reward function, which is the closer the agent is to G, the higher its reward is. For example, plus 10 for cells 1 hop away from G, plus 8 for cells 2 hops away, and so on. And the output of the MDP is the policy mapping from the state space to the action space. So these are the inputs, and that is the output of the MDP. Now, when we use the MDP for reinforcement learning, we give to it only 3 of the 4 inputs. We give it the state space, the action space, and the reward function. We do not give it the transition function. Okay? The output still has to be the same, which is the policy. So the objective, or one of the objectives of reinforcement learning, is to learn the transition function first. That is how the model behaves, and then use it to learn the policy. Now, to learn the transition function or the model, there are 2 classes of reinforcement learning algorithms that are there. The first one is called model-based algorithms, which reconstruct the transition function for every state and for every action. Of course, this is the time-cumbersome procedure. So instead of model-based methods, the other type, which is model-free methods, are also used, which is they do not construct the full transition function. They just take samples of the transition functions at the states that matter to solve the problem. Most of the commonly used reinforcement learning algorithms use model-free methods. For example, you might have heard of QLearning. That's a model-free method. Okay. Another one, SARSA, model-free again. Now, within model-free methods also, there are 2 types. One is called value-based methods. QLearning, for example, is a value-based method. The other is policy-based methods, which do not care about reconstructing the values or the utilities at the different cells. Rather, they directly try to learn the policy. The actor-critic learning method is a policy-based method. Okay. So let us do a quick review of the value-based methods, and then we will talk about policy-based methods. We will review a value-based method for RL called QLearning. Now in QLearning, the inputs are S, state space, A, the action space, and the reward function R. The transition function is not given as an input, and because QLearning is a model-free algorithm, it will approximate the transition function. And to do this approximation, it builds a data structure called a QTable. The QTable is indexed by the cross product of the state space and the action space. For example, in our grid world example, there were 64 states corresponding to 64 cells, and the robot could do 4 actions at each state. So this would give 256 state action pair combinations. So that's why the QTable would have 256 rows. The contents of the QTable is what is called the value. It is initialized to any random number. It could be initialized to 0. Here I show it's initialized to 0.2. Now let us see how the QLearning algorithm works. So the main operation inside the QLearning algorithm is to update the values inside the QTable. And so it does this by visiting different states of the problem and taking different actions at each state. This is called exploration. And basically an exploration takes the form of a state action sequence. For example, initial state S1 followed by the action A1 at that state S1, followed by next state S2, then A2, and so on. This gives a sequence of state action pairs. This sequence is called an episode or a trial or even a sample. And each SI-AI pair is called a step. And at each step, the Q value inside the corresponding row corresponding to that state action pair is updated using the equation that I show out here. This is called the QUpdate function. And this is repeated for multiple episodes. The stopping criteria of the QLearning algorithm is when the value inside the QTable does not change significantly, and this is called convergence. So for example, if our initial QTable was the one that is shown on the left, duplicated from the last slide, at the end of the algorithm, the top of the QTable could look something like this. So for here example, I show that the Q values have changed to different values, and the highest Q value is for the action east. So that basically shows that when the agent is at coordinate 0, 0, the best action for it to do to reach towards the goal is to do east. This is the pseudocode of the QLearning algorithm. The QLearning algorithm that we have talked about so far is the shallow QLearning algorithm. It's suitable for smaller state and action spaces. If you have to scale up to a higher dimensional space, then a deep QLearning algorithm has to be used. Deep QLearning came around in 2014 and 2015, so it's been around for a much lesser time than the regular QLearning algorithm. In deep QLearning algorithm, as we said, it has to scale up to higher dimensional spaces. What would be an example of a higher dimensional space? Suppose we have a robotic arm that needs to learn how to move in order to grasp or pick an object. These type of robotic arms are used by online e-commerce companies. Amazon, for example, uses robotic arms to pick and grasp objects. In fact, if you're familiar, there is a challenge that Amazon runs called Amazon Pickup Challenge, where you exactly have to do this. Make a robotic arm learn how to pick up objects from shelves. So for doing tasks like this, deep QLearning is used because the state space and action space of this robotic arm can be very high dimensional. So the main change that is made from the shallow QLearning to deep QLearning is that the QValue function that was there in QLearning, that is now learned using what's called a function approximator. So it's written as Q of SA and the parameter theta. Now, in order to implement this function approximator, a deep neural network is used. Now, using the deep neural network introduces a challenge, which is a deep neural network is essentially a non-linear function. And if you have a non-linear function and you use it for QLearning, there are three main issues that can happen. First is there could be correlations between sequence of observations. That is, if you do 2 or maybe more successive trials or observations, they might be very close to each other. And so the Q values are not being updated significantly through these trials, which amounts to loss of computation, loss of time. Second problem is that small updates to Q values could significantly change the policy and therefore the data distribution. The third problem is that there could exist correlations between the Q values and the target values, meaning that the values that this Q table is initialized with, those might have an effect on the final values that are being learned inside the Q table. We don't want that to happen because the final values should depend on the task or the problem that is at hand. So to solve this, two techniques are used. The first is experience replay buffer that randomizes over the data and removes the correlations between observations. And the second is the iterative update technique that removes the correlations between the Q values and target values. Let us first look at what the experience replay is. Now, in the regular QLearning, we had seen that a trial was a sequence of state action pairs. In deep QLearning, a state is defined as a sequence of state and action pairs. It's now called action observation pairs, denoted by XIAI. And now this tuple of state, action, reward, and the next state is called the experience. A sequence of experiences is stored inside what's called an experience replay buffer or a replay memory. Another aspect is that if you have worked with deep neural networks, you know that the input layer is of a fixed width. So basically the observations or experiences that you get have to be a fixed length as well. So what is done in deep Q networks, you truncate the experiences to a fixed size or a fixed width, correspond to the width of your input layer of the deep Q network. Now this is the architecture of a deep Q network that was used to learn to play Atari games, and this is the corresponding picture showing the architecture. Now let's take a look at how the training of the deep Q network is done. Now this is very similar to the learning in the QLearning algorithm, the shallow QLearning algorithm. Remember, there we use the QUpdate function in order to update the values inside the Q table. So here also we use a function very similar, or an equation very similar to the QUpdate function. But instead of using Q values, what we use is a loss function, which is shown by this equation out here. And then we use the gradient of this loss function with respect to the parameter theta I. And this gradient is what we use to update the Q function. The other difference is that whereas in the shallow QLearning algorithm, we used trials in order to update the Q values. But here, instead of taking trials from the state and action space, we refer back to the experience replay buffer. And we use the observations from that experience replay buffer as our trials to calculate these loss values and find the gradient. And finally, as I said, we use this gradient to update the Q function. So this is the full algorithm of the deep QLearning training. Here is a graph that shows the improvement using deep QLearning over traditional or shallow QLearning applied to learning to play Atari games. And as you can see, there is a pretty large improvement, almost 1000 times for some of the games that you get by using deep Q networks, where the blue bar is showing the deep Q networks performance improvement. So to sum up, there are two main concepts used in deep Q networks as opposed to regular or shallow Q learning algorithm. One is you parameterize the Q function using the parameter theta, and then you use a deep Q network in order to learn this function approximator for the Q function. And experience replay buffer and iterative update are the two main concepts which are used inside Q networks in order to update the Q values. Of course, as you understand, deep Q network is a very large topic, and it's not very feasible to complete it within a few minutes of lecture. So I have given some resources. There are many tutorials available online, many online resources which are excellent reads. So I highly encourage you to explore on the internet a bit more about deep Q networks if you're interested, and then you can find a lot of resources. I've given some of the resources here, also given references to some texts. The most important text being the one that is given at the top here by Sutton and Bartow. That is the seminal text in reinforcement learning, and it gives a very good introduction to Q learning. In summary, Q learning and deep Q learning are value-based methods. They are both model-free algorithms, and they are basically suitable for scenarios, for state and action spaces which are discrete. In contrast, if you have continuous state and action spaces, then value-based methods cannot be used, and you have to use policy-based methods, which we will talk about next. But before doing that, I want to take a few minutes to talk about the summer internship program at NRL. Some of you might already be familiar with this. This is an 8-week research internship at NRL and also at other Navy labs and centers. The major criteria is you must have completed the 9th grade, must be at least 16 years of age, and to work at NRL, US citizenship is required. There are several areas at NRL that students work in. I, for example, work in AI, ML, and computer science. There are several other researchers who work in AI, ML, computer science too. And beyond computer science, there are several other topics. Many engineering disciplines, space sciences, radar, acoustics, chemistry, and so on. I have given several disciplines there. You should check out NRL's website to see which other disciplines NRL is interested in. Please keep in mind that the deadline of application is fast approaching. It's November 30th, and more information is available at the website that's given at the bottom. Having said that, let's move on to policy-based methods. As we start with policy-based methods, let's do a quick recap of what we have learned so far. We have seen that a policy denoted by pi is a mapping from the state space to the action space of a problem. We have also seen that value-based RL like QLearning works by approximating the policy using a table. In policy-based methods, instead of making this table which approximates the policy, we directly approximate the policy pi. And just as we had done in the case of QLearning or deep QLearning, we approximated the Q function using the parameter theta. Here also in policy-based methods, we'll approximate the policy pi using a parameter which we again denote by theta. We also define a performance measure for the policy-based methods denoted by j of theta, and we require that this function j of theta must be continuous and differentiable in theta. Let us delve a bit further to see how policy-based methods like the policy gradient methods work. So this method comprises of 3 steps. In the first step, we generate samples with the current policy, and we initialize the policy as a random policy, just as we initialize the QTable with random values. In the next step, we determine what the expected rewards from the generated samples from step 1 are. And finally, in step 3, we update the policy parameter theta using the rewards from the samples gotten in step 2. And we keep on repeating this until, like QLearning, we reach convergence. Now let us see how each of these steps work. So the first step is to generate samples. Recall that in QLearning we had said that a sequence of states and actions is called a trial or an episode. So we will use the same concept here of trials in the problem space. Basically, a trial is a sequence of states and actions, and now we'll go ahead and calculate the probability of a certain trial. Now on this slide, I have done some math to show how the probability of a simplest trial, just a 2-sequence trial, can be calculated. Basically, what I show out here is that the probability of the trial can be calculated from the parameters that are given as input to the RL, basically to the MDP underlying the reinforcement learning problem. And that's what I show at the bottom of this slide. Now with this idea, we can extend this 2-sequence trial to a 3-sequence trial now. And likewise, we could extend the probability calculations for that. Once again, we see that you can calculate the probability of a 3-sequence trial from the input parameters to the problem. So basically with that idea, we can say that for a trial of any length, we could calculate the probability of getting that trial. And that's what I show by the equation at the middle. Now, having understood this, let's go one step ahead and see what the goal of reinforcement learning is. Remember, we had said towards the beginning of our lecture that the goal of reinforcement learning, or the output of reinforcement learning, is a policy that maximizes the reward. Let's now apply that same definition to policy-based methods. Remember, in policy-based methods, the policy is approximated by the parameter theta. So in policy-based methods, the objective of reinforcement learning becomes to find the best or optimal value of this parameter theta that parameterizes the policy. I denote that by theta star, and theta star can be calculated as that expression given on the right hand side at the bottom. So what is that expression? Explain that here. It basically says that find the policy parameter theta that maximizes the reward from the trials when averaged over all the trials drawn as per the trial's probabilities. So basically this is doing just what reinforcement learning wants to do, which is finding a policy that maximizes the rewards from trials, and basically doing this to the parameter theta that guarantees that the policy calculated using the parameter theta guarantees the maximum reward. Next, let us see how the third step of the policy gradient algorithm is done. Note that at the top of this slide, I have rewritten the formula that I had at the bottom of the last slide, and now I have marked the expression after the argmax using j of theta. Recall that j of theta was the performance measure for the policy that we had defined. Okay. In our next step, we slightly simplify the j theta. So here what I'm doing is representing j theta as a sum of the rewards over the different trials. Here I is the index of the trial and t is the index of each step inside the trial. The next step would be to find the first derivative of j theta with respect to theta. I've shown the math out here, but on the next slide I show what is important. Basically at the middle of the slide, the red colored rectangle shows that I can find the first derivative in terms of the sum of the rewards, which is the green underlined part, and the first derivative of the log of the current policy. Now both of these parameters, the reward at each step inside a trial and the log of the current policy, is available to me, and I can find the first derivative of the log of the policy, and from that I can calculate first derivative of j theta. At the bottom I show the policy gradient algorithm called the reinforce algorithm. This was the first policy gradient algorithm proposed in the late 1980s. It has the 3 steps shown in the picture on the right hand side, and which we have been talking about for the last few slides. The first step is to sample a trial using the current policy, in other words, run the policy. Then I use the reward from that policy and the first derivative of the log of the policy in order to calculate the first derivative of performance measure j theta. And then I use the derivative from step 2 in order to update the policy parameter theta. And I keep on doing this until I can no more improve the policy. That is, I have found the optimal value of the policy parameter theta. This is the pseudocode of the reinforcement learning algorithm. It's exactly what we had seen with the 3 steps on the last slide. Just here, notation wise, I've replaced the sum of the rewards using the symbol g of t. Finally, I would like to talk about an RL algorithm called actor-critic learning. Till now, we have learned about 2 types of RL algorithms. The first one was the value-based algorithms like QLearning, and the second one was the policy-based or policy gradient algorithms like the reinforcement algorithm. Now in actor-critic learning, these two types of RL are combined. So one component of actor-critic learning, the critic, implements the value update algorithm, and the other part, which is the actor, implements the policy update algorithm. Now the actor-critic learning algorithm runs very similar to past algorithms. So basically first you do a trial or you take samples from a sequence. You get the reward from the steps of that sample or trial. And then you use that reward first inside the critic to run a value update equation, which as you see is very similar to the Q value update equation we had in QLearning. And then we take the output of that value update part, which is this parameter delta, and we use it in the actor for the policy update equation in a manner very similar we had used the first derivative of the performance measure J in the reinforcement algorithm. So basically the important thing to keep in mind is that the policy gradient part, which is the actor part, where you calculate the first derivative of J theta, that basically determines what algorithm you are using. Okay. So different values of that parameter can give you different flavors of this actor-critic learning. So here I show some examples. So if my first derivative of J theta, inside that, if I use the sum of the rewards, which is generated by G of t, I get the reinforced algorithm we had seen a few slides back. If I define that as a parameter called QW, I get a type of actor-critic called QActor-critic, where you are doing the critic part using the Q value update. If you use a function AW, which is called the advantage function, which is shown out here, we end up getting what's called the advantage actor-critic algorithm, or A2C for short. And finally, if we use just delta as we saw in the last slide, we get temporal difference actor-critic algorithm. A very commonly used algorithm under actor-critic is called advantage actor-critic, where we use the advantage function that is shown on this slide. If it's single thread, it's called advantage actor-critic or A2C for short. And if it is multi-threaded, which is you have several threads running in parallel, you end up getting what's called A3C or asynchronous actor-critic algorithm. So these two algorithms are widely used now in many reinforcement learning tasks. Remember, because there's a policy update part, so it is suitable for continuous policies as well. This is the pseudocode of the Q actor-critic algorithm. You can go through it. You can see it has the critic part followed by the actor part, where the critic part is similar to the QLearning value update part, and the actor part is similar to the policy update. And here is the pseudocode for the TD actor-critic algorithm. I'd like to wrap up by talking about two variants of the policy update algorithm. One is called the proximal policy optimization or PPO, and the other is called trust region policy optimization or TRPO. So the main problem addressed here is, as trials are being done in the policy gradient algorithm, the next step might end up in a low reward state, which is falling off the side of a cliff while climbing it. And this can be fixed by adjusting the step size. And these two algorithms, PPO and TRPO, they basically give different methods to adaptively adjust the step size. And there's a very nice overview of PPO, which is available at this link out here. I've given some resources out here for reinforce and actor-critic learning. You should explore this at your own time. In today's lecture, we have talked about reinforcement learning. We have seen value-based methods like QLearning algorithm and policy-based methods like the reinforcement algorithm and actor-critic learning. As you might understand, I have compressed about 3 or 4 textbook chapters and several research papers into 30-minute worth of lectures. So if you plan to use these topics in your research, it would be a very good idea to explore the links that I have given at the end of the different topics. As always, I am available to answer your questions. My email is given on the first slide of this lecture series. So I thank you and I hope to see you for our next lecture again. Bye.